Hello, we're going to solve this exercise in Leet code that has a medium difficulty and is basically using the breadth first search algorithm. Here we have a binary tree, and the idea is to do the level order traversal and return the list. So given a root of a binary tree, return the level order traversal of its node values going from example from left to right, level by level. So this is by nature using the binary tree, in which case we are here in the node, in which we are in the level 0. So we have the number of nodes corresponding to the 2 to the power of the level. So 2 to the power of 0 is 1. There we will go kind of like a zigzag way. Going to the next level, we will go like 9, then 20, and then we go to this node, like to this level of with these nodes here, and the level 2. So to the power 2 we have 4 nodes, and 3 we have null we don't have nodes in like we don't have leaf nodes after the 9 node. So this will be the what we will return. We will return the root, in which case we will be in the level 0. We will return 9 and 20 as we will be in the level 1. And in the level 2, we will return 15 and 7 as is the only nodes that we have. And then we will return the null that we will have after 9. This will be useful, for example, in hierarchical data processing or, for example, in GPU size scheduling, where we have memory hierarchy and in the operations. So as we have to traverse the tree level by level, we will use the algorithm breadth first search, in which case it depends on the width. If we will have a perfectly skewed tree, we will have only nodes in one of side, only one side of the tree, in which case we will have basically a linked list, and we will have ON complexity in the burst research. In the worst case scenario, which is we have a perfectly binary tree, we will have O to the power ON complexity. If we wanted to use the depth first search, we will have the difficulty that we will have to go in depth first in this um, in the right leaf, and then going to the first to the left, and then going to the all the way to the right in all the depth, and then we will have to go back and kind of have to like, figure out the level order traversal. But with breadth research, we will have this naturally, so we will go with this algorithm, in which case we will use a queue in a FIFO way to do this instead of the recursion that we will be using in the first search. Um, we're gonna use the approach of um, using this data structure, the queue, in order to do the operations, in which case we will have constant time approaching to this, and we're gonna do like the size-based approach. To explain the size based approach, we will just count the number of nodes in each level to start doing the operation. So we are in level 0, we will only have to do here, like we will only like process this node in breadth first search, and then we will go to the child nodes. So here we will be in level 1, in which case we will have 2 leaves, 2 nodes. And then we will go to the next level and we will process 4 nodes and so on and so forth. So this is the approach that we're gonna follow. To start with the solution, we are first gonna observe one of the cases, in which case the root is empty. We will have to return an empty vector. So in this case, if root is empty, return an empty vector. This will be the first case. And as we are doing this the size-based method, this will also be applicable if we only have only one root node, and that's it. So here we start. We're gonna create a matrix vector, as we can see here. That is what we will return as the solution. We'll have integer nodes, and this will be the result. That is what we will be returning in our solution. Here we could start and initialize the array with some amount of elements in the vector, in which case we can see the nodes are in the range of 0 to 2000. So we could initialize this, in which case we could already access members in the vector. For example, doing the following, we could start initializing already the vector and accessing the elements. But this is inefficient, as we will have to do reallocation. We will already allocating elements in the container. Even if we don't need the 2000 elements, we will be allocating them. So this will be kind of a waste. Another approach that we could do here is use reserve. So we will reserve the memory for 2000 nodes, and we are not initializing them. So if we access them, we're gonna get an error, but we are not using the entire space. We are only allocating the space to eventually insert elements with pushback, which could be more memory efficient in this case. Then we're gonna create the queue that is gonna store the tree node type pointer just to traverse the the binary tree, and we're gonna start pushing the root. To start the algorithm, we are going to do the algorithm and the conditions while the queue is not empty. In case it's empty, we just get out of the loop of the breadth first search. So as we are doing the level size approach, we are gonna get in from our queue, we are gonna get by level how many nodes are we processing. So if we are um, basically in the first level, we are just gonna get here that we only have one element so far, and we are gonna get level size equals to 1, as we only have the root node that it will be 3 first. Then we are gonna process all nodes at current depth. So we are gonna iterate this. From the current size, the current level, we're gonna get the current node that we are processing. We're gonna create it in the variable current node. That will be the front of the queue. This will be in this case the root, and we will take this element out of the queue. So we are not processing anymore, and we are just getting the current node in this variable that we will get the front of the queue because it's a FIFO, first in, first out. And similarly, here we are going to create a vector that is going to store the node for the final solution. That is current level, the current level with the nodes that we are processing. So to initialize the current level, we are gonna reserve this for the level size. This means that in the first iteration, we will only be reserving for the current level just one for one node. If we will be in the next level, then we'll be reserving for two nodes in this case. After this, in the current level, we will insert with pushback the current node, and we will insert its value that is from this member of the structure. And then we will be enqueuing the children for the next level processing. We are gonna start processing with the current node that we already like have the pointer to that, so we're gonna access the left member. We are gonna push the current node. We're gonna start from the left. And we have a child from the right. Either way, we're gonna insert the current node in the right. So this will be basically the algorithm. As we see in the second iteration, we already enqueued the left child, which will be 9, and the right child will be 20. So in the next iteration, Q already popped root, so it will be only 2 elements. This will be in this level. And for each level, it will start with 9, for example, this is already enqueued. And it's also stored in the variable of level size. So for each of these, we will get the front for the current node, in which case it will be 9 because it was inserted first. So it's the logic of the FIFO. It will be stored in the current node, and here we will like dequeue the 9, for example, from the list, and we will insert its value that will be 9 in the current level in that later is going to be our results in the level order traversal. As we don't have left or right children, we will just like go to the next node. It will be 20. We will get this current node 20. We will insert this value in the current level, which will be the traversal. In the current level, this will be a vector basically, and then we will have these two children. So then we will go to 15 and 7, and they are null, so we couldn't insert anything left or right, and we are out of the loop. So at this point, as we are out of the loop, um, we just need to insert um, first the the members that we already traversed. So in our result, we will have to push back a vector containing the elements that we already traversed. In this case, in the first level, just 3, in the next level, 9 and 20, and then 15 and 7. So what we will push back is this vector that is the current level, and we will use the semantics with move, so we avoid doing a copy of the whole container. and we could insert the level traversal in this array. Finally, we use return the result vector, and we're going to upload our solution. Here we have a typo. Here's the solution. We see in our runtime the complexity. This will be ON. This is a binary tree, and which will depend on the number of, like the width, so the number of nodes. And we can also see the complexity that is ON. Thank you so much. That will be the solution.